welcome back. I'm really glad some of you made it from the lunch break and sun back into the dark planetary, the dome stage. So I'm really happy to be here now and introduce and soon hand over to Mikhail Kokorich. I'm not sure whether many of you know him. I just recently learned about him, and he is, just to give some context, named kind of the Elon Musk of Russia. And although you're not really from Russia, you were kicked out from Russia because you were maybe too successful as an entrepreneur. And the same thing happened with the United States because of the background, in fact. And now you're in Europe and you're building the at least third big company, and or even two maybe. But I assume about one you will talk more. And so whatever I heard about you was very impressive, and your current project with Destinus is incredible. And yeah, I leave the stage to you to tell us more about this project.
Thank you for the introduction. And yes, I have this like a funny title of the guy who was not wanted in Russia and the United States, in both countries, which is I think it's quite difficult to do. So I moved from Russia, I think already 12 years ago, so after before the Ukrainian war, and spent 10 years in the US, building several companies with a different success, but last company became finally public with all this like bumpy road. And yes, since last year we've been building the new company here in Europe, and we have team distributed in several places. By the way, we have pretty large team here in Munich also, in Switzerland, in Madrid, and now a little bit also in France. And what we try to do, we are trying to merge rocket technologies inside the aeroplane, inside the aeronautic. So we can build a plane which can fly as fast, almost as fast as a rocket. So this is not a new idea, and actually Germany, the was of the fatherland of this idea, with a Zanger and with all this. So we really try to build this rocket plane, which use hydrogen as a fuel, both for air-breathing engine and for rocket engine. And here's like a small video that basically shows what we are doing, and shows some prototypes that we are flying, and our team. And then I can maybe tell a little bit about technology, and then welcome to have questions. Yep. So.
Since the beginning of the space age, or I mean, since the beginning of aviation, actually people were thinking, okay, in order to fly faster, you need to fly higher.
This is a supersonic plane, right?
They are flying subsonic and subsonic speed. And supersonic will like extremely loud.
Could you explain how it works?
Yeah, it's a mix of an airplane and a rocket. We call our vehicle near space vehicles, hyperplanes.
Hypersonic aircraft is something difficult to achieve.
So we start by putting together an excellent team, finding experts in various areas that can help us get to the first stages of prototyping.
We've somewhat adopted the Spotify model for managing our engineering. Fundamentally, it's about putting very small teams together. You define what these teams are doing, and you let them go.
This is more or less like a development of the very complex software, where instead of delivering a huge piece of the code, you're basically doing this with multiple iterations.
We like to build things and see how they work.
So we will begin by building small vehicles and prototyping small vehicles that will be flying in subsonic speeds.
So after going subsonic and learning how to operate those machines, with the pilot in the loop first, then we go with autopilot and autonomous GNC solutions.
Because Destinus is a vehicle without a pilot, the vehicle will just fly through those points and go and land where it has to land. Automating the whole thing and making it fly by itself.
And then next year we will also have a vehicle that is designed for supersonic speeds. We're still going to be producing noise when we take off and land with the ATR engine, but these noise levels won't be much louder than existing aircraft today.
We will need a lot of suppliers, quality raw material that we can use in our manufacturing process. We want to do the quality control, the assembly, the engineering in-house in Destinus.
Everyone's happy when you show progress, right? So, even if it's small subsystems and things like that, right? It shows progress to everyone and to investors.
Yeah, well, what we're developing is really something that is necessary for the future, both in terms of delivering cargo at a very, very fast speed, and then also on the clean aviation aspect.
So hydrogen is a fuel of the future. It's not even like a fuel, I would say it's a carrier of the energy. So you can transfer energy from solar panels or from nuclear reactor to the tanks of the cars or the planes or hyperplanes.
We will have zero carbon emissions with the Hyperplane network that we will be offering.
We need like something like 10 hubs globally.
And then implementing the infrastructures for the hydrogen refueling activities and the maintenance of the hyperplanes.
So logistics, it's enabling. It's not only part of economy by itself, but it's changing the life. The system was moving even before aviation, so any new way of transportation just open new possibilities.
Yes, and we actually using hydrogen not because it's green. I mean, it's a good outcome, but hydrogen is a very nasty substance to use in aviation because of the density and the low temperature, because you can use it only in cryogenic form. But because hydrogen is the best carrier of the energy, so the fuel efficiency and specific impulse of high-speed air-breathing engines that using hydrogen is much higher than for kerosene. And when you fly for a long distance, which makes sense for hypersonic aviation, these get you winning on a mass several times, so you will be much, much lighter. But the second advantage of the hydrogen, that hydrogen is one of the best thermodynamic, the coolant liquid. In order to heat 1 kilogram of hydrogen from cryogenic temperature to 500, 600 C, you need to spend more than 10 megajoules of energy. So you can use this to cool your structure, you can use this to cool stuff in your engine, you can pass the energy from one part of your vehicle to another, and it enables many things. And without hydrogen, this type of the high-speed aviation, it's actually much more difficult to build. And we somehow rely on the future where the hydrogen finally will be available in the airports, initially in maybe some bigger hubs, and finally in smaller airports, so we can operate it everywhere. So now we are flying our subsonic prototypes, and we are developing our first hydrogen aeroturbo rocket engine. This is a new cycle which uses the rocket cycle for the turbine. Basically, the turbine is not using external air, but use only the hydrogen or hydrogen oxygen from the tank to rotate it with a gas generator. And the rocket engine, hydrogen or cryogenic rocket engine, which can finally move at the speed up to more than 10 of Mach. A lot of cool developments. It's like around 80 people. We a little bit older than 1 year. Pretty well funded. Like we raised from the beginning almost 35 million euro. So it's not bad for the early stage company. And have a lot of people both from aeronautic, but also from rocketry, and also from re-entry vehicles. So this is an interesting mixture of the people because so many technologies came from classical rocket industry, but still it's a plane. And somehow like the only vehicles where people mastered flying hypersonically, this is re-entry vehicles. And probably I would stop at this point, and I'm happy to answer any questions about technology, how we build a company, how we use Spotify model, the actually software model, to design hardware, how we try to do this between different countries, which is a separate task. So happy to answer any questions.
So someone has a question. Can you hear me, actually? No? So maybe you need Switch the mic, yeah. So if you have questions, please raise your hand and ask. So maybe I start and then I go around, yeah. So prepare your questions and keep them in your mind. So, I mean, why didn't this happen in the past? You said the idea is old, yeah. It comes actually from Germany, which is great to know. But why hasn't this been realized before? And then maybe you can also talk a little bit about the key technical challenges. So you talked about re-entry. So I assume heat will be an issue if you go hypersonic and you have friction with the atmosphere. Then really dealing with these crazy temperature differences. You speak about hydrogen as a coolant, but also as a fuel. So the engineering challenges sound dramatic to me. So maybe you can also talk then secondly about that. So why hasn't it been done before? And maybe are there also others that try to build something like that? And what are the key challenges from an engineering point of view?
Yeah, that Germany, it's a place for the birth of many great ideas. Like in aeronautic, we know this. So it's definitely here the heritage of this one. Especially this technology is pretty historical. But actually, the first type of this, for example, engine was built but was never flown by Kelly Johnson for the predecessor of SR-71. They've been building this aeroturbo rocket engine cycle for the vehicle that they've been thinking that could fly with this high supersonic, hypersonic speed. But at that time, they decided to move to the kerosene engine because to have availability of the hydrogen in all places, in all battlefields or somewhere where they fly SR-71 was almost impossible. Yeah. And also material technology was different. So over the years, the people was trying to come back to these ideas. Actually, a couple small companies even build small prototypes in US, in Huntsville, Alabama, where is the center of this, founded by Vernon von Braun, by the way. But nobody actually did attempt to build a really flying engine. So, and I think the reason why the first, now we see that commercially it can be feasible because the hydrogen was not available. Even now, let's put this way, it's not available. Now overall production of the hydrogen for mobility, maybe a few dozen tons of hydrogen per day. And it should be produced by thousands of tons per each airport. So the scale of the changes should be like in the last century when the kerosene was used only for lamps. And then in 10 years, after invention of the combustion engine and the conveyor, the consumption of oil increased 10,000 times. So it's quite probably to happen the same with the hydrogen. And this is only happening now. Let's put it this way. If we started 5 years ago, 10 years ago, it would be too early. So now the hydrogen is available. On technical problems, let's put it this way. We for sure have a lot of areas where we need to break the boundary for engineering. We're not trying to make some scientific level inventions. So we're relying on something that was tested in the different industries. For example, in our aeroturbo rocket engine, the turbine, the expander turbine, which uses hydrogen for the rotation, it's actually the same type of the turbine that used for Vinci engine for upper stage in Ariane, or for RL-10 engine for Centauros upper stage, or RD-146 in Russia. So kind of people build it, master it for decades. And hydrogen used for the cooling in power plants, in nuclear power plants, for generators, also for decades. So we as humans know how to use this pretty efficiently. And we can move using, like, for the structure, pretty simple construction materials, like stainless steel, the nickel alloys, and basically use hydrogen to cool it. So we don't need to put any ceramic tiles, something that can be fragile or, with a limited lifetime.
Yeah, hi. So I wanted to ask you about what you mentioned at the end. What were your developmental challenges? So your prototyping approach, and also small teams works very smoothly when they are co-located. So how do you handle, let's say, development over countries? Do you split departments over countries?
Yeah, this is both good questions. The prototyping and iteration, we really try to build iterative approach. So rather than just put a design for the big plane, big engine. We're just building. So we built our Alpha 1 prototype, which was like a 7-meter long. Now we flying the Alpha 2 prototypes, which we had like an even hard landing. We fixed it in 2 months. We again flying this. Now we're building Alpha 3 prototype, building the Gamma prototype, which will fly supersonically, already with a, not turbojet engine, but with an ATR engine. We're building the first ATR engine, which is a pretty small, like 5 kilonewton, half a ton thrust, but it will be the first ATR. We're designing the first rocket engine, also pretty small, like 30 kilonewtons. They're building the tank, so really with a multiple iteration. So we kind of flying this year dozens of times with our prototypes. And also this is how a company is built. The problem of the geographically separated teams, it's a really big problem. Yeah. So and this is like common knowledge that yeah, startup need to be in the same place. In my previous company, we've been all in a Silicon Valley Bay Area in Santa Clara, and we built like basically from scratch in one place and grow until we make an IPO in one place. But in my business career, I passed 2 times 1,000 people in my companies. So one company reached 10,000 people. And you know what? After you 500 people, even when you are in one place, you're already not talking with each other. So you are in different floors. People actually don't know each other. They never meet with each other. So you face the same problems, but a little bit later, when your corporate culture is already settled. So for us, from the beginning, we need to resettle the culture, which allows this a lot of horizontal connections, a lot of like the work on a very flat structure with a lot of ties between the teams. And from the beginning, it's very hard, but we create a corporate culture from the beginning that will allow us to grow. And this is what we try to do. It's not easy to work with a horizontal company because a lot of noise. Yeah, you know the hierarchy, this like a hierarchical management always easier. Yeah, this Ordnung, you know that who is responsible for what. No, when it's like horizontal, the people sometimes doing the same job 2-3 times, but it allows you not to fall into the, like some dogmas or some mistakes. We use this like what we call Spotify model. You can Google this called Spotify engineering culture, and actually it's very applicable for hardware companies. For example, Jet Propulsion Laboratory using the same approach for the building this Mars rovers, this one. So all work divided to small teams, multidisciplinary teams, which actually like a small companies. And then all the disciplines, it's organized in chapters, engineering chapters. And then you do this with basically the design loops, which we have in our company 8 weeks design loops. And we try with these design loops, always synchronize, use these loops to reshuffle between the company, make resynchronization. And this allows us to move very fast. So for the 1-year company, we start to fly our first plane in 4 months since we started the company. Now we have fully autonomous landing, takeoff. We're building engine, 1 engine, 2nd engine. We almost built our test tent with liquid hydrogen, which is like unbelievably fast. It's only because you just allow people to do it. Yeah? I met before I left US, with Gwen Shotwell and asked and kind of talked. Yeah, you always had the best engineers in SpaceX, and she told, "No, Michael, we never had the best engineers. Best engineers until recently was going to Raytheon, Lockheed Martin, GPL, Boeing. We've been like a scrappy company, no money, crazy founder, like a strange, but the people who come to us was not the best, but we allowed them to do the crazy things. And we underestimate the power of the people if they say, hey, just do this. The average age of the engineers who was building Apollo program was 28 years old. And the primary major was not aerospace. Aerospace didn't exist that time. It was agriculture machinery. In Russia, the first engines for the moon, like a rocket, was built by Nikolai Kuznetsov, who was designer of the diesel engines before. So we are different in a way, so we really let people to make crazy things, make mistakes. A lot of like sparkling, a lot of like hard discussions. But it allows us to move very fast.
Okay, more questions. Actually, in the meantime, why do you think Europe is a great place to build this? So I understand in the United States you can get a lot of money. Typically, aerospace is prone, or you are somehow in defense, always active, and Europe is not the greatest place for that. So how do you finance, and why Europe?
Defense-wise, I mean, yes, Europe is much more modest. I mean, now probably after Ukrainian war, it will be more money. That's what we see. Great interest to our technology. Money-wise, to raise actually no difference. After coronavirus, I raised my pre-IPO round $200 million for previous company, sitting in my room, basically, just making all the roadshow online. So now I raised, for this company, we raised money. I didn't meet with almost anybody face-to-face. No investors, I didn't meet with them. It just was through Teams and Zoom. So and Europe is great because it's not so many companies. You can get really good talents. Many, much more diverse. Many countries. It's a 500 million population. More open, less craziness with this stupid ITAR, CFIUS, all this American bullshit. Yeah, because they are really this very defense-oriented, and this basically this shit ate American aerospace. Unbelievable. Yeah. So Europe is much more open. This is a much better place to build.
Okay, hi. So I think we all agree on the advantages of hydrogen. I think using it to cool your engines and re-entry and so on, and also the weight advantages are pretty clear. But how do you tackle the density disadvantage, which is you need 4 times as much space to carry so much hydrogen?
Yeah, I mean, this is a really big disadvantage because the density of the hydrogen, 70 kilograms with with some oilage, it's 65. So it's 14 times, 50 times less than kerosene. And even it's more efficient by weight with factor maybe 3, 4, 5, depends on emission, it's still more volume. And unlike in a normal plane, your volume of the fuel is just 10% of the volume of the plane. In a supersonic, hypersonic cruiser, your volume is 50 to 70%. So basically, you are flying fuel tank. Yeah. So it means you need to build this in a different way, where the fuel tanks is a structure, like in a rocket. Yeah. So whereas the fuel tanks is a structure, it actually the structure. But the problem is that in the rockets, the first rockets are usually flying only up. And Starship is doing many maneuvers also, but usually going up. In rockets also cylindrical. Yeah, cylindrical is a good shape. Here you have actually the blended, this blended shape. And here you need to move to something which is called tensegrity structure, where you have tensegrity elements, the conformal structure with tensegrity, like in a dirigible. Again, look in a Zeppelin, the German heritage. And it's actually flying dirigible. We call even this prototype Zeppelin. Yeah, so we're pressurized. And pressure is creating the structural stiffness. It prevents from the bending. So it's pressurized structure, but with multiple tanks inside, we have many cool things, and it's a really structural conformal tank, which is a holy grail for this type of the things. And the structural coefficient should be between the rockets, which is 10% usually, and the planes it's 30 to 50. So our goal is to be within the 20. So if 20, we can easily close the mission for a hypersonic cruiser flying from here to, let's say, Buenos Aires in 2 hours.
Okay, thank you very much. I was just reminded that we have the time done, and we start also with the next panel. Thank you, Mikhail.
My pleasure.
Great to have you here.
Thank you.